We'll set the scene initially, though, by perhaps having a brief revisit in terms of muscle mechanics, just so that we're understanding fundamentally what is happening in terms of parameters such as force velocity relationships, and also the notion of the way we have rate coding and size principles. So we'll start off with this basic premise here, which is taken from this reference that's provided. And what we have is we have our panels. On the x-axis of this graph to the left, you can see the loading grams. Remember, what we have here is these are very, very small muscles that have been identified, so hence the loads are very low, and they're also isolated muscles. What we then got is on the y-axis, we've got the shortening velocity, and that's in units here, it's centimeters per second. And what we can see is a classic force-velocity relationship, or in this case, a load versus change in length over time. So it's again, it's force, velocity, load against time. And what we can see is, as we understand, is that we get this standard relationship that you see here, which fundamentally, when the load is low, so we've got a low load, we have a very high rate of change. So the centimeters per second is very fast, it's rapid. But as the load that's being applied to the muscle is increased, we start to get this hyperbolic almost. It's not quite hyperbolic, but we start to get this hyperbolic-esque relationship. In other words, as the load increases, the change of centimeters per second, that is the velocity of shortening in this case, starts to decrease. And that is the relationship that you'll remember, which defines a concentric muscle action. And we can see this on the panel to the left. Here what we have is slightly reversed in terms of the way it's being presented. We've got the speed of contraction here in centimeters per second on the x-axis. And then on our y-axis, we've got the force, in this case, in newtons. And we can see here, this is our concentric panel, or a concentric response to the left. And you can see, as this graph here is identifying for us on the left here, you can see in this response to the right, you can see that as contraction speed increases, the amount of force being produced decreases. So in other words, it's just perhaps a real world example of this idealized graph that you can see over here. What you will also notice, though, is that when we look at the y-axis, notice that the way in which the speeds have been represented, they go in opposite directions. And that is simply to represent the notion of shortening under concentric and lengthening under eccentric loads. And what you can see is under eccentric loading that the relationship is very, very different. That fundamentally, as the speed of contraction increases, the amount of force being produced, in this case in newtons, also increases. And that is what we see under eccentric loading. And you go, well, why is that the case? Why is that? Well, of course, the difference is these are accelerational forces. These are deceleration or braking forces. So if we've got to put the brakes on in a car, we're going at high speed, we've got to push harder on the brakes than if we were going at low speed. It's the same with the way the muscle produces force. If I have to put on a very, very, have to decelerate very rapidly for whatever reason, it might be a change of direction, as we've seen in a previous session, which is on change of direction measures. If that's the case, and fundamentally I need more force to be able to slow the body down before I then accelerate. So how does that then relate to what we see perhaps in terms of the muscle actually directly in action? Well, as I've got here, in concentric mode, the peak power is at a velocity of 1/3 to 1/2 from maximum. So the peak power, here's the power on the graph here, and what we can see is there's the peak power, and it's about 1/3 to 1/2 of the point in terms of the relationship between velocity and force. So again, here's our concentric relationship. We know that the mechanical power is lowest at the two extremes of the force-velocity relationship. In other words, when we're under very, very high loads and we've got no change in velocity, then the amount of power being produced is zero. The reverse is also true. When we're under very low loads, but we're at maximal shortening velocities, then again, mechanical power is near as damn it, zero. But under eccentric conditions, so here's our eccentric curve here, so here's our mechanical power that we're going to look at, and here's the force, so this is our force-velocity relationship. As we've written here, in eccentric action, the peak force increases initially above the isometric maximum. So that's quite interesting, that we know that generally maximum force occurs isometrically, but actually initially we get an acceleration under eccentric, which is potentially above that. And to a certain degree, a function of increase in stretching velocity. The resulting mechanical power shows dramatic increase in the early part of the eccentric phase. So look, you can see that the force actually starts to level out, but the mechanical power increases dramatically. Remember that fundamentally, under eccentric loading, what you're looking at is, as the velocity of shortening increases, so does the amount of force needed for the braking